So I think we'll start. First of all, welcome back, everyone, to Lecture 2. Before I begin, a couple of you have asked me about lecture notes. So like I said yesterday, I will post lecture notes to my webpage, and I'll also share them through the organizers somewhere central. Those lecture notes, however, are not posted yet, so I need to finish typing them up based on my chicken scratch notes that were, in fact, so like I wrote messy lecture notes in PDF, realized, wait a minute, I hate lecturing from like my laptop or from a tablet, and I like scribbled everything handwritten, and now I need to go back and like clean up the type notes. The trouble is, any hour I spend typing those notes while I'm here is an hour I don't spend like actually interacting with people here. So it'll likely be like I'll finish all this up on my flight home this coming weekend, and so and if you don't see lecture notes from me somewhere like usable by like Monday, you have my full permission to email me directly and like all caps be like, where are those lecture notes? I will not be upset at you. Okay, so we left off yesterday afternoon having set up this notion of the stochastic block model. So let's just refresh our memories here. We'll write that A is a stochastic block model with a probability matrix B and community memberships tau, right? We say that B here is going to be a symmetric matrix of probabilities, right? And then tau is going to be like tau 1, tau 2, blah, 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 up to tau n, right? And all these tau, this is in like a big vector of the integers 1 through k to the n. So for every one of my n vertices, I'm going to look up its community membership in this vector tau. And once I know those community memberships, the edges, which again, remember A here is our adjacency matrix. The entries of A record which pairs of vertices are forming edges. The edges are going to be drawn independently, conditional on B and tau, according to Bernoulli with probability tau I, tau j. Okay, and the important idea here was that the SBM kind of extends the Erdős-Rényi random graph by making the giant leap of saying, instead of having only one kind of vertex, we have k kinds of vertices. Okay, so there are k different ways that a vertex can behave. And if you want kind of the intuition behind this model, think of this as like humans in a social network. We have k different groups corresponding maybe to like interests, right? So we have a community of computer scientists and a community of mathematicians and a community of football, soccer fans, a community of other football fans. That was an America versus English joke. Right? So, and you might preferentially talk to people within your own interest group or whatever, right? Okay, so once I know what community you belong to, though, I know exactly how you will behave stochastically, which other vertices you are more or less likely to form edges with. Okay? Part of the reason why we like using this adjacency matrix is that if we introduce one more character to the plot here, right? We have a matrix Z, binary matrix here, n by k, and the ith row of Z, so something like Zi, if I may, or maybe Zi dot is better, right? All right, here, I'll just write it this way. Zik encodes whether the ith vertex belongs to community K or not. Okay, so I have a big matrix Z. Its rows encode the memberships of the vertices, and the reason we like that is that now I can write that the expected value of A, right, under parameters B and tau is just Z, B, Z transpose. Okay, and we kind of ended our lecture yesterday by saying when B has a community structure, it ought to be the case that we can look at the leading eigenvectors of this matrix and read the community memberships off of them. In the simple case of two communities with balanced sizes, that was especially easy. The second eigenvector of this matrix is just plus or minus 1, according to whether you're in one group or the other. Right? In more complicated settings, right, when the community sizes are different or when B has different properties, it's not going to be quite so simple. We'll have to look at the top k eigenvectors of this matrix. Right? But it will still be the case that some kind of community structure is encoded in that leading eigenspace. Okay? And then we started talking about how, well, of course, in real life, right, I don't get to see this, right? I see A. Okay? And so I want to reiterate the statistics problem, like the problem of inference is like running probability in reverse. I don't remember what textbook I'm stealing this from, but right, probability theory studies how you go from a model to data, to a random variable, right? You discuss, I draw a random variable from some model and I want to say things about its properties. Statistics concerns running that machinery in reverse. You show me a random variable, some data, right? And I want to figure out what model it could have come from. That's inference. Okay, so again, we said that kind of the two key inference tasks here are estimating B and tau, and most of the time we care a little more about tau than B. So in the statistics parlance, B is like a nuisance parameter. A nuisance parameter means a parameter you have to estimate just as a side effect of figuring out the thing you really care about. Of course, there are situations in statistics where we actually do care about B, but most of the time we care about recovering these community memberships. Okay. So, I want to talk for most of today's lecture about how we can make this model a little less unrealistic. Okay, so there's always this tension in statistics between models that are easy to analyze, models where we can do enough probability theory to actually say something about how A behaves when it draws from this model and how I can go from A back to this model. Right? So on the one hand, I want to work with models that are easy to analyze. On the other hand, in the end, we're going to try and pretend like real data. Like we go out in the world and we collect data, and we're going to pretend like that data is A. So it better be the case that the model we're working with is expressive enough to produce random networks that look like what we see out there in the real world. Okay. Has anyone ever seen a real world network that looks like an SBM? There are like a handful out there you can like kind of squint and be like, yeah, sure, maybe, right? But like it's pretty unbelievable, right? Okay, let's think about, I'm going to keep calling it Twitter because I'm not going to make a political statement. Let's imagine Twitter before all this stuff, right? Okay, and when I was the grad student's age, like the most followed person on Twitter was Justin Bieber. And I have no idea where he ranks now, so let's just pretend it's 2014 and I'm a bright-eyed, idealistic grad student again, and Justin Bieber has like 30 million followers on Twitter or something. Okay, and the next most followers was something like a fraction of that. I don't remember. I wish I could remember now who was like the next most followed person on Twitter back in the day. Okay, the point is you look on any social network and you look at who are the highest degree vertices. They are orders and orders of magnitude more popular than any of us. Right? If I draw a network from the SBM, that doesn't happen, right? Basically, all of the vertices are going to have degrees of about the same order, right? So that looks wildly different from what we actually see in real-world networks. Okay? This is true even outside of social networks. You might think, oh, well, that's just this degree heterogeneity phenomenon, we call it. Maybe something unique to human social networks. It seems not to be. We see what are called power law degree distributions all over the place, right? And even in places where like it seems like there's no reason it really ought to be there. So one shortcoming of the SBM is that the degrees kind of look silly. So let me start making a list here. Like, what don't I like? And I'm sorry, you were getting glommed into this like you were going to have to not like the same things that I don't like. We're in the same block of the SBM today. Okay. That's a question, don't we like? Okay, so one issue, degree heterogeneity. See, how is my spelling of Greek-derived words? Heterogeneity. If I didn't get it right, we can fix it in post, right? Is that a thing we can do? Never mind. Okay. Right? The basic problem is that under the SBM, all vertex degrees, and just as a reminder, right, that's di, that's the degree of the ith vertex, sum along a row of A, are all basically the same. Okay, Okay, they're at least all kind of the same order. Let's think of another problem with this model. Let's imagine for a second that indeed everyone belonged to one and only one community. Did anyone here only think about mathematics? There are some of us, I know. Like, some of us think about mathematics and football, right? So it would be nice to have a model that allows us to kind of capture the fact that, in truth, most people belong to more than one community. Most vertices are going to have some behavior that looks like community 1, some that looks a bit like community 2. We want to allow for kind of mixtures of community membership. Okay? So another thing that I, and therefore you, also don't like about this model, I'm sorry you're getting dragged along for the ride, is that somehow, let's say sort of the problem, this is kind of usually called in computer science, we talk about hard assignments. Of the vertices to communities seems I don't know, unreasonable seems like a weird word to use. Seems bad, I don't know. Suboptimal. Okay. I'm going to leave space here for one more thing that we don't like. We're going to come back to it at the end of the lecture, because if I say it now, we're going to spend the whole rest of the lecture talking about it, and I mean, that's fun for me, but not for you. Okay? Okay, so lucky for you, or for us, I was still saying the royal we here or something like that, right? Both of these problems have been addressed by a handful of extensions of this model. I'm going to talk about those now. And one thing I'm going to highlight for you is how, as we make those extensions, that identifiability problem we talked about. Remember, I can relabel the entries of tau here. If I permute the numbers 1 through k, I don't really change anything about the model behavior except for the labels that I put on the communities. Okay? That kind of non-identifiability is going to keep showing up, and it's going to keep getting worse. But it's going to keep getting worse. It's going to keep getting worse in a way that we still don't really care about. Okay? But so it's going to be a problem we have to keep track of and be aware of. It's not going to bother us when it comes to actually applying these models to data out there in the real world. Okay. So I'm going to start with this second issue first, just because it's an easier model to talk about. So to fix this problem, right, the fact that in the SBM every vertex belongs to one and only one community, we're going to do something simple. We're going to say, okay, well, now every vertex is going to belong to a convex combination of the communities. Okay. This is going to be called the mixed membership SBM. Okay, and this was first presented by Edo Eroldi, David Bly, Steve Feinberg, and Eric Xing, 2008. I think it's a paper in JMLR. Don't quote me on that. So the idea here is going to be, instead of assigning every vertex one and only one community membership here, we're going to relax the rows of Z from being one-hot encodings, like being corners of the simplex, to being any point on the K simplex, or the K minus one dimensional simplex that sits in RK. Okay, so we're still going to have our B here, be K by K and symmetric, right? But now we're going to have, let's say Zi is going to sit in the K minus one dimensional simplex. Okay, so it's going to encode a probability over 1 to K. And now when it comes time to generate an edge, I'm going to do the following. Instead of just looking at the community memberships of one vertex and the other, I'm going to repeatedly randomly assign, based on Zi here, your vertex to one of the K communities, randomly assign the other vertex to one of the communities, and use the entry of B that I find. Okay, so like you and I both have some probability vector over the different communities, like how much you like math, computer science, football, I don't know, swimming, whatever, list your like communities that you might belong to, right? And then we both have our vectors in the simplex that sort of capture to what extent we belong to these different communities, and then when it comes time for us to form an edge or not, we're going to randomly pick among those communities, and based on what we both find, look at the corresponding entry of B, and that's going to be our probability. Okay? Maybe said better in math than in words, my edges are going to be independently drawn according to Bernoulli B. That's a terrible K. No. Z-I-K. Okay. And I'll just note, like for those of you who prefer, if you're like me and you prefer matrix vector kind of notations, this is just Zi transpose B. Okay, so the story really is two vertices, I and j, both randomly choose from among the communities that they could belong to according to their vectors in the simplex, right? After they've chosen their random memberships, they form an edge with probability BKL. Okay. Right, and so, please forgive me for repeating notation. The expected value of A with these parameters is Z, B, Z transpose again. Okay, so I understand this Z and that Z aren't strictly the same, but like this Z, its rows are in the simplex, they're just at the corners. This Z is just a little more relaxed, more chill. Come on, that was actually a funny joke and no one laughed. Okay, so this model inherits the non-identifiability we mentioned in the stochastic block model, right? If I relabel the communities here, I'll never be able to kind of tell different relabelings apart. The exact same thing happens here, right? Okay. But again, that's okay. That usually doesn't bother us because we don't really care about the communities themselves or what we call them, right? Call them 1, 2, 3, 4, 5, call them A, B, C, D. It doesn't matter, right? We care more about the equivalent structure that it puts on the vertices, right? It's going to tell us which pairs of people belong to the same community or not. There's a second, sneakier non-identifiability. And think of it this way. If I'm not careful, what can happen is that I have all my rows of Z here, all of my points on the simplex, and they're arranged in such a way that I could, if I were clever, rotate about the all ones vector, or reflect about it, right? In such a way that after that transformation, all of my points are still in the simplex. Okay? Let me say that again. You could imagine a situation where if we're not careful, I have all my GIs in the simplex, but I can apply a transformation that rotates and or reflects the points around the all ones vector. So everything stays in the simplex, but suddenly I've applied this weird orthogonal transformation that keeps the all ones vector fixed. Okay? And that's a problem, isn't it? And that's more of a problem than this relabeling issue, right? That could mean that there are multiple different assignments of all of us to communities, to like what combination of communities you belong to, multiple such assignments that are wildly different and are not just related by a permutation of the labels, right? That all give rise to the same model. Okay, is everyone more or less with me here? Like, this is a technicality and it's going to get worse, so like, I don't want to dwell on it too much. If you want to kind of, and we'll see another example of this where things get even worse before the end of the lecture. If you want to see more about specifically this issue, so specifically the issue that arises here in mixed membership models, the term to Google is the pure node condition. Right? One way to avoid this worse, like weird rotate within the simplex issue is to demand that at least for every community there exists at least one vertex whose zi is in the corner corresponding to that community. Right? So if I had, for every k, I had some I such that the ith row of z is just 0, 0, 0, 1, 0, 0, 0, right? If every corner of the simplex had at least one zi there, then you couldn't do this silly like rotate around the simplex in a weird way trick, right? You could still permute the labels. You could still apply a permutation to the basis axes, right? And like you could move the simplex around, but all you'd be doing is it would be relabeling the communities. Okay. So this is the pure node condition. And if you want to see more about this, see, there's a couple of papers. I'll mention two of them here. Jin, Tracy Ke. That's from 2017. And there's also work by Yuan Zhang and some other folks at Michigan. Uh, 2020? Yeah. Okay. Okay, I've run out of space to write, but I'll also mention work by Purna Sarkar at UT Austin, who also has a paper from around the same time looking at this. So again, just kind of an annoying technical condition, but I want to stress that this is a technical condition that really does matter in a way that this community relabeling issue really doesn't matter, right? The relabeling the communities doesn't bother us. The idea that you could like take all these points and move them around in the simplex in a way that gives rise to like meaningfully different choices of z, that should bother us. Okay? And if you're not quite grokking this idea yet, that's okay. We're going to see an even worse version of this kind of non-identifiability soon. Okay? Well, okay, even worse in the sense that like you have even more ways to screw things up, but in ways that are not going to bother us in that case. So, okay. So this is a model that fixes point 2 here, right? We've relaxed these hard assignments of vertices to their communities to what the computer scientists would call soft assignments, right? You belong to a sort of convex combination of the communities. Let's address point 1, degree heterogeneity. And the idea here is, well, okay, if all the degrees are the same and we don't like that, let's correct the degrees. Okay? We're going to make some degrees big and some degrees small while keeping this notion of community structure. Okay? So we're going to look at a model where we're back to having tau here. Everyone's going to belong to one and only one community. But now everyone's going to have another parameter called their popularity parameter. Every vertex will have a popularity parameter, and if that parameter is big, the degree is going to be bigger. You're more likely to have friends. Must be nice. That was also a good joke. Come on. Okay. Right, so this is the degree corrected. Degree corrected SBM. Okay, and this is due originally to Karer and Newman in 2008. Oh, excuse me, not 2008. What am I saying? 2011. Okay. Although I should acknowledge that if you go and read that paper, the original, the way they parameterize this paper in the parameterize this model in the original is a little different from what we're going to see here. It's just sort of different in, I don't know, more a matter of degree than kind. Pardon the pun. Okay, that one didn't deserve a laugh, so that's okay. So again, we're going to have vertex communities tau 1, tau 2, tau n. Okay, so we're back to having hard assignments of vertices to communities. Everyone belongs to one and only one community. Okay. And then we're going to have a vector of popularity parameters, theta. And that's going to be in non-negatives to the n. Okay, and this is going to be called the popularity parameter. Okay, and then we're going to say now our Aij, our edges, are independent, and they're Bernoulli. And it's still going to depend on the community memberships of I and j. So vertices I and j form an edge with probability that depends on their community memberships. But it's also going to depend on how popular they are. Okay? So if vertex I is very popular, is more popular, has a larger popularity parameter, then this probability is going to be bigger. Same goes for vertex j. Okay? So we still have community structure. It's still driven by the structure in this matrix B, but now every one of our vertices is more or less likely to form edges based on a sort of idiosyncratic parameter for each of them. Okay. Like in statistics language, we would say there's an effective vertex. Okay. Question?
Is your graph directed or undirected?
It's undirected.
Okay, but do you know what conditions you have to have so that the graph exists?
So the graph exists.
Yes.
Maybe I should clarify. This is always for I less than j. Does that help?
Okay, but you can have one person with infinite popularity and everyone else with zero.
Yeah, so well, if you really want to be a stickler here, if you want to remove this, your concern is like, what if everyone has theta 0 and like one person has a huge popularity? Yeah, I mean, we're statisticians. We usually assume these kinds of weird edge cases away. But you're right. So you're also getting at a more important point, maybe. What if the thetas are so big that this product is bigger than 1? Right? That's sort of the opposite problem what you're talking about, I think. Right? But like, there are some problems that could happen here if we're not careful about how the thetas are chosen. Everyone with me there? Right? So I think the next thing I'm going to say will help answer your question. And if that's not the case, raise your question again. So, first of all, there's a non-identifiability still because of the fact I can relabel these guys. Right? That hasn't gone away. There's another actually very annoying identifiability problem. If I scale all of the thetas up by some parameter, and I scale b down by that parameter squared, right, I have the same model. The probability stays the same, right? So now I can't tell the difference between a network where everyone is very popular but b is small. I can't tell that apart from a network where no one is very popular but b happens to be big. Right? Okay. Now, I'll say this kind of like, let's list the non-identifiabilities. Right? Okay, there's relabeling. We don't really mind that, right? Can scale theta or b. That's annoying, but we can get around it by basically demanding, for example, that these thetas have some fixed average, like maybe they average to 1 or something like that. Okay. Then it's not quite a non-identifiability, but like we have to make sure that for every one of these things, theta I, theta j, B. We have to ensure that these things are actually probabilities, or else things don't make sense. I mean, you can get around these things by saying, like, okay, I'll take truncate this to 1 if it's too big or something like that. There are ways to get around this. Okay. I'll point to, so if you want to see kind of one of several ways you can get around this, maybe I think the kind of most cited paper related to this model is by Chao Gao and co-authors. There's one more on that paper. It's 2017? 2018, excuse me. Now, did that partially answer your concern? Like maybe not. You're still making okay. And so again, if you we usually will keep this, but it is frequently the case that we're going to think about these thetas as coming from some IID from some distribution, and so like the event that they're equal to 0 is going to have it won't always happen, and there won't be some kind of like weird all 0 graph or anything bizarre like that. But one always has to kind of be careful of these weird edge cases. As statisticians, we usually just kind of like make a convenient choice or assumption so that those edge cases don't happen. There's a question, or?
I guess it's sort of a stupid question, but like, it seems like those theta i's, theta j's, like, at least say it could be the case that they're like significantly larger or have significantly more difference than the difference between entries in the beta and B.
In B.
And then it seems like, like the individualism will be sort of like have a stronger effect, maybe even than the,
Yeah.
stronger.
Yeah, so I think what you're worried about is like if we weren't careful in how we chose these things, right? I might be in the situation where the thetas are of such a higher scale than B that they kind of get swamped. And that's why I mentioned like we usually make an assumption about, typically it's something like that, these things average to 1. So we're going to make, we have to do some kind of assumption like that just to make sure that we can even identify the model, right? So I can always, again, we can always take the thetas and scale them all up by like alpha. And if I multiply all the entries of B by 1 over alpha squared, the probabilities don't change, right? So that's, and again, that means there's an infinite collection of different choices of the parameters that give the same distribution over A, which we don't like. So we're going to make some kind of an assumption to fix it.
Like whether or not individuality is sort of stronger than the effect of individuality is stronger than the effect of like groups.
Right, but you could make the other, like, you could have the exact opposite problem by, saying, like, I don't know, fix how the entries of B behave versus the thetas. So once you make a decision, then you're kind of making all your inferences modulo that decision. But yeah, you're right, that kind of tension is kind of baked into the model. Once again, I would maybe point out that like the thing we care about more is not necessarily estimating B and theta. I mean, it's useful to know which vertices have really large values of theta. Those should correspond to the vertices with high degree in our network. So it's like the theta should carry some kind of information about who are kind of the hubs of their communities, right? But I wouldn't get so hung up on, interpreting these parameters beyond knowing that they are parameters that kind of control your average propensity to form edges, right? Does that help answer your question?
Yeah.
Okay.
It's just, in some senses, it feels like degree heterogeneity is not as much maybe a problem, like all mathematicians don't have friends or something, that sort of thing.
No, so I would say, in real world networks, this degree heterogeneity problem really is a problem, right? It really is an issue, right? Yeah. Even for networks of mathematicians. I want to be very clear, I'm like, occasionally I make fun of mathematicians and probabilists and combinatoricists. It comes from a place of love. Like again, most of my graduate courses were in like theoretical computer science and like I took a bunch of combinatorics and probability classes. Like I promise I'm not like, I don't know. One always risks making these jokes of like someone not understanding that like the joke is coming from like friendly ribbing, not like trying to be mean. So I want to go on record. Right, like without good mathematicians, we don't know what we're doing with, like we can't do anything with these models, right? So, okay. I want to mention one other model without going into great detail. I just want to give a shout out to, so there's, like without going down the rabbit hole, but see also, there's the popularity adjusted SBM. This is due to Srijan Sengupta and Yuguo Chen. In 2018. Okay. It seeks to solve a problem kind of related to this degree heterogeneity problem. It does so with a very different kind of approach, basically by like punching holes in B in a clever way. It also gets at the issue of sparsity, which we'll talk about more today. Okay, so I just want to mention that there's another model that tries to fix this, does so in a very different way. It's complicated enough that it would take me 15 minutes to set it up, and we only have like 35 minutes left, so I'm going to just kind of mention its existence. I encourage you to Google it, especially because like, it's a very good paper, and we're going to breeze right past it otherwise. Okay. Should also acknowledge the kind of obvious thing on the board, or I don't know, obvious in the sense that mathematicians mean it, which is like if you go and like scribble for a minute, right? I can combine these two models, right? I can have these degree heterogeneity parameters, and I can have mixed memberships, right? So I can have degree correction, thetas, and I can have Z be this nice simplex kind of structure. So I can have both degree correction. Boy, I picked a bad piece of chalk today. Change up. I can have both degree correction and mixed memberships, and then I get the degree corrected mixed membership stochastic block model, the DCMM-SBM, which is an acronym that only a statistician could love. Okay, but one can do all this, and did I not write down who originally did that paper? Well, anyhow, so if you Google that, like it's in a paper somewhere. Okay. And like, I don't know, it's the obvious thing to do, but like, obvious is in quotes, like getting those non-identifiabilities to be handleable and making sure that you can still do inference in that model is not a trivial task, right? But it's obvious in the sense of like, if you read these two papers, then you were like, I'm going to write the follow-up paper to these, there you go, right? Okay. And so if you're a statistician, you are constantly saying to yourself, but like, what if I could generalize this further? Because presumably, real-world networks still don't come from anything like these two models, right? Like nature doesn't know what these thetas could possibly be. So let's generalize things a tiny bit further, and then I promise that like this last piece of the board will be the most general model we're going to talk about, and then we'll spend the last bit of the lecture sketching how we would go about inference in all these models, and especially how we'll recover tau. And we'll talk a little bit about the third mystery problem that I left blank at the bottom of the board there. So, generalize more. Question mark? Right. Let's notice something. In all of these models, we have something like expectation B and Z, and this Z could be, these memberships. It could be the simplex, the simplex vectors. I'm sort of agnostic here. And here, just to make, I think to make things clear, I'm going to call this Z tilde. The tilde is there just to stress that like it doesn't have to be this Z or that Z. It could be something a little weirder. It could be like Z left multiplied by a diagonal, a matrix with the thetas on the diagonal, right? Scale up all the entries. Okay. But for some choice of Z tilde, all these models look like the following. Z tilde, whoops, B, Z tilde transpose. Okay. Right, so Z tilde here could be, for example, Z tilde equals, so big theta times Z. I'm sorry, I didn't write it on the board, but if you take all this vector of thetas, put it on the diagonal of capital theta, like capital theta here, it could be like the diagonal matrix with the thetas on it, right? Right, Z tilde equals 1 hot encodings right? So Z tilde is one of the kind of Z-like matrices over here. Right? So if we're generalizing this a little bit, all these models kind of look like this, right? For some kind of clever choice of z tilde. Okay? And bear with me temporarily while we make this assumption. If B is positive semi-definite, I can write something like this. Okay, so like let's pretend for a minute like we can take the square root of B. I promise we'll assuage ourselves that that's not really a problem soon. Right? Just imagine how we can do that. Okay. Then I can write all these models in kind of this way. Okay. So I took that Z matrix, and then I took this K by K B matrix. Z is n by K. B and its square root are both K by K. So this is like I'm taking B to the 1/2 and applying it, or it's transposed, but they're the same because B is symmetric. I'm applying B to every row of Z tilde. Right? I'll just write here, like Z tilde B 1/2 equals like B 1/2 Z1 transpose oh, sorry, those are tildes. Okay, so I'm going to think of like each row of Z tilde times B to the 1/2, in some sense, encodes the behavior of a vertex, right? So if I tell you the ith row and jth row of this vertex, you know the expected value of Aij. Okay? Again, if I look at the ith row and jth row of this matrix here, take the inner product of those two guys, that's exactly the probability of Aij being 1. Okay? So in some sense, I'm just going to write like rows of this matrix encode vertex behavior. Okay, everyone more or less with me here? So this fact is the intuition behind a yet more general model, which takes all of these as special cases, provided we can take the square root of B. Okay. Motivates a model near and dear to my own heart, just because it's what like my grad school group worked on. So like you're going to hear about it. You're going to hear about it more from Jesus and Joshua. Such is life. Okay. The random dot product graph. Okay, RDPG for short. Okay, this is originally posed by Young and Scheinerman in 2007. Okay, we also have, okay, this is, I think, the only time in all of these lectures that I'm not going to write out all the authors on a paper. So in JMOR in 2018, Avanti Athreya and then a whole mess of us from Johns Hopkins have a survey paper about this model. So like there's, I think, like 8 or 7 authors on this paper. So like I'm not going to list them all. Daniel Fishkind, Min Tong, Carrie Priebe, myself. I'm sure Vince Lazinski. Am I missing someone obvious? Jesus, you guys know. I'm embarrassed that I can't like just recite all that author list off the top of my head. Anyhow, like original paper with kind of the most recent broad overview of the model, and then I'll also mention, just as a side note, or you know what, I'll leave the side note for the end of writing this out. What's the idea here? We're going to choose. So we're going to kind of abstract this idea that the rows of Z tilde B 1/2 here encode vertex behavior. So we're going to choose a bunch of vertices, a bunch of vectors, x1 through xn in Rk. And we're going to do so in such a way that their inner products are always probabilities. Okay? And then we'll do just like we've been doing in all these other models, independently for every pair of vertices, I'll find their corresponding vectors. And we call these the latent positions. They're latent variables, one for each vertex. And that point in k-dimensional space encodes kind of how each vertex behaves. So the latent positions of both vertices I and j, we'll take them, we'll form their inner product. We get a probability, because that's how we chose the x's. We'll flip a coin that has that probability of success. If it lands heads, we'll put an edge between I and j, and if it lands tails, we won't. Okay? So let's just note that so long as this B matrix is positive semi-definite, this recovers all of these models as special cases, right? Just by choosing your x's in a kind of clever way. So, so maybe point 1. All of these previous models on the board are special cases. If B is positive semi-definite. Secondly, if B is, indefinite, there is a model that sort of allows for these x's to not all have, to kind of still recover all these other models without needing this this semi-definiteness requirement. So this is the generalized random dot product graph. Basically, what that model is going to do is it's going to replace this inner product between xi and xj with an indefinite inner product. So I say xi transpose a big diagonal matrix with ones and negative ones. Right? So instead of xi transpose xj, I have xi transpose, we'll call it like IPQ, right? It's a like an identity, but some entries are ones, some are negative ones, okay, and then xj on the outside. Okay, that's no longer an inner product. The geometry of these points gets kind of complicated and weird, but again, as far as things like recovering these x's and doing inference, most of the same results I'm going to tell you about in the next couple of days go through. So this is the generalized random dot product graph, and that was worked out in a paper by Patrick Rubin Delancey, Joshua Cape, who you'll hear from next week. I'm going to run out of board. Min Tong and Carrie Preeb. Can I fit that on the board here? I want to make sure that's all the authors. Yes, it is. It's 2022. I'm sorry that corner of the board is so unreadable. Questions so far? Okay, so we started with the SBM. We said this model is kind of silly. And we've repeatedly kind of said, what are some of the shortcomings of the SBM? We addressed some of them by kind of expanding the model. And then we said, wait a second, at this point, why not just let this animal here be whatever, just arbitrary vertices, excuse me, each row be arbitrary vectors. I'm sorry, say again, that B is greater than?
Yeah, because there are two parameters, kind of the within community connect.
Yeah, so if you're in, so I mean, to be clear, so Roberto's question is kind of in two parts. So if you think about the case where B is like P on the diagonal and Q off the diagonal, right? As long as P is significantly bigger than Q, right, then that positive semi-definiteness is fulfilled, right? Just by like Gershgorin disk theorem or one of these kind of things. More generally, right, you need to just look at the structure of B, right? I mean, if we fit this model to data, we're probably not going to find that all the on-diagonal entries of B are the same, right? So then you need to be a little, you're just making an assumption. And if you're not willing to buy that assumption, or you just think it's not a reasonable one for your application, then you'd want to go to this more general model. And I will try and make time on Friday to talk about, like, in the end, someone's going to come to you with like a network that they, like a scientist went out and like did data collection and like got a network, and they're going to come to you and say like, model this, like fit one of these models to it. And the first question you have to answer is like, what model you're going to use, right? That's the problem with model selection. It's very hard. In fact, my advisor told me not to think about it until I have tenure, so I'm mostly not going to talk about it this week, but I will talk about it briefly on, most of Friday, right? Because it's a very cool problem, and if ever there's an excuse to talk about it, it's like in an introductory level lecture. But I'm going to repeat my advisor, Carrie Preeb's advice to not think about model selection until after tenure. But you can lecture about it, I guess, is the rule that I'm making up. Yeah, in the back.
I guess it's worth commenting on the fact that, making a connection with Ether's course, which is that Ether is talking about random geometric graphs. And, random dot product graphs are, not quite the same as random geometric graphs, but they're quite similar. And especially if you take the latent vectors on the sphere, then, whether an inner product is large or the distance is small, it's kind of the same thing. So, yeah, there's lots of connections between the two. And, another difference, for instance, between, more probabilistic point of view and statistics point of view is, in probability often there's a hard thresholding, right? So there's connection if and only if the vectors are close. But, you can relax that and consider soft random geometric graphs where there's, additional randomness involved, and then that gets you closer to this statistical perspective. So there's lots of connections here.
You literally said like the next point I was going to make. So no. Thank you. No, I don't have to say it. So as a remark, right, if I think of these points, right, like so I think Dieter has not yet spoken about kernels, right, but could imagine a situation where my kernel for any 2 points in my random geometric graph is just given by the inner product. So now the one difference here is that whereas in the random geometric graph, right, I'm going to just check whether this inner product is bigger or smaller than some threshold. Here, it's still going to be that the presence or absence of an edge is probabilistic, even conditional on this information. So you can, if you squint, you can think of this model as being like a noisy version of the random geometric graph, right? It's like I look at how far apart 2 points are, and then like, okay, there's an edge or not, and then maybe I flip the edge on or off. Okay. So we have about 20 minutes left, and I promised that we would talk about one more problem with these models, so we're going to come back and do that. Let's see. I want to keep that, and I'm going to erase everything in between, so everyone gets a 30-second breather here. Okay, so in the RDPG, there's still a non-identifiability. And like I mentioned, it gets a little worse in one way. Like it's more complicated now than just shuffling labels, but it's still going to be a non-identifiability that doesn't really bother us. Let's notice the following. Expectation of A when I have latent positions x, so x here is going to be n by k, right? And like, say that x transpose ij are all probabilities, just as a reminder. Okay, this now equals x X transpose. And if I multiply by the identity in between, for any orthogonal Q, so if Q is any k by k orthogonal matrix, I can always multiply by the identity in here. And now so now I can't tell the difference between the latent positions X and the same latent positions all hit with the same orthogonal transformation. Okay? So I can only ever hope to estimate these X's. Remember, in statistics, we always want to observe A and figure out what model gave rise to that A, right? Or at least make a good guess, right? And if I try to do that, I'm never going to be able to recover beyond that non-identifiability, right? I can't tell the difference between some set of X's and the situation where they've all been rotated or flipped or generally messed about in an orthogonal way. So the best we can do, we're going to want to find an X hat. So I've already kind of alluded to it, but this is convention in statistics. When you have some parameter and then you want to estimate it from data, you put a hat on it, right? So X hat is my guess as to X, usually based on some data. The idea is going to be that we get an A, it's generated from some true X. We're going to pass it through some algorithm of some kind, which is going to remain a mystery for now. Out the other end comes an estimate of X, so it's X with a hat on it. Okay, we want to find an X hat such that we have to minimize over all of these orthogonal Qs, right? We can never recover, we can never tell the difference between X and X Q transpose. So we're going to say, okay, modulo that non-identifiability, I want to minimize the distance between my X and my guess of X and the true X, again, up to that orthogonal non-identifiability. We're never going to be able to get rid of this, so we're going to incorporate it into our measure of how good we're doing. Okay? Saw a couple of people furrow their eyebrows. Let me say that again. We, in the end, are going to want to say, I give you some data. I hand you a matrix A, a network A. And you hand back to me an estimate of the X that gave rise to it. Right? That's inference, right? I give you data. I give you a random variable. You tell me what model produced it. Right? Or you tell me what parameter produced it. Okay? How do we evaluate how well we did? Well, my answer is this. Right? I can only ever estimate X up to this Q, so I'm going to incorporate it in how we assess our performance. This should kind of look like, in a very vague sense, the way that we had to incorporate that minimization over permutations when we looked at the agreement, right? If I have a stochastic block model and I try to figure out what the taus were, I have to account for the fact that I might have relabeled, right? I don't want to penalize our estimator just because it called group 1, group 2, and group 2, group 1, because it learned the same equivalence class. Same idea here, right? We're only evaluating ourselves up to some notion of recovering something up to an equivalence relation. Okay? Another question should be, or rather, one thing I haven't said is what norm should this be, right? So I'm sorry, I should have put this here immediately to make sure no one thought it's oh, that's a spectral norm or something. There's a big question mark here. Okay? So this is a point we'll come back to tomorrow. Okay? Maybe, well, okay, we'll see how we do. Maybe I'll at least set us up today. Probably not. Okay? So we need to still specify what norm this is going to be, but modulo that, our evaluation here is going to be up to this equivalence notion, up to the fact that I can never tell the difference between X and XQ, how well did we recover X? Now, we need to be maybe a little bit careful lest we hoodwink ourselves. I want to point out one problem here. Right, so again, let's all just kind of mentally bookmark this decision. Right? We're going to come back to it. But so far, we've been talking about recovering x here, right? And the intuition is somehow like, well, if this were a stochastic block model, then x really should still contain some kind of information about the community memberships, right? If this really came from a stochastic block model, then XX transpose should just be like the big Z, B, Z transpose matrix. Right? So like, I'm going to write something like XX transpose just equals ZB Z transpose under the SBM. Everyone more or less okay with that? Right? If the truth is the SBM and B is positive semi-definite, then we can pick the x's in a clever way so that this equality is true. Okay? Now, yesterday, we looked at B equal to 1 over n times like P, Q, Q, okay? And now, we have that the expectation of A is like X transpose, or X1 to Xn are in Rk. Now, usually, under the random dot product graph and kind of other related models, x1 to xn are IID sum f. And this f doesn't change in n, typically. Okay? And the problem is that then, therefore, like basically the scaling of x transpose, let's put it this way. The smallest eigenvalue of x transpose is going to grow linearly. Okay, and you can see that, for example, by like if these x's are IID from F, right, the sample covariance matrix and this matrix of outer products, like this thing and x transpose x have the same non-zero eigenvalues, right? So the smallest eigenvalue of this and the smallest non-zero eigenvalue of this and the smallest eigenvalue of x transpose x are the same, and the sample covariance matrix converges to the population covariance. Don't worry, like those details are in the lecture notes, not worth doing here. Right? It's like one of those things where like if you write it out, you're like, yeah, that's obvious. So there's a problem now, and that's that unless we do something clever, the scaling of this guy doesn't match the scaling of B that we were studying yesterday. We need to scale this back down in some clever way. Okay, so that's issue 1. Right? So we need to rescale. And what we're going to do is imagine that we're going to take XX transpose and just multiply it by a scalar that is getting small. So instead, we're going to look at the expectation of A under X, and I'll write rho and we're going to let rho is going to depend on n in 0 to 1, and rho is down to 0. Okay, so we're going to have, this is called the sparsity parameter. Okay, and ideally, if we wanted to match our friend B from yesterday, we're going to need to let rho be basically like 1 over n. Okay? And I alluded yesterday to how there's a kind of a gap between spectral methods and things like belief propagation for estimation here, And that's basically that if you take rho to be 1 over n, spectral methods tend not to quite get where we want them to be. They usually don't get something like agreement going to 1. Okay? But if we allow rho to be like log to some power n over n, everything's usually okay. So the gap is big if you're a probabilist or combinatoricist, right? If you're a statistician, that is to say an applied probabilist, I will just repeat the fact that there are, I think the factoid that always floats around is that there's like 10 to the 90 particles in the visible universe. So like log base 2 of everything that exists is like 300. And so log n is a constant if you're a statistician, right? Okay, right, that was one of those jokes where like I say it with love. I myself have written papers where like the triumph of the paper is like we got rid of a log factor. So I'm not denigrating the work that goes into that. I've written such a paper myself. But for purposes of like how much does the rest of the world care outside of people in places like this room, like that log factor really shouldn't bother us. Like it shouldn't be the thing that stops us from handing these tools to an actual scientist and telling them to use them, right? Like we shouldn't say, oh, there's a log factor on this and therefore we can't share it with the world, right? That's maybe holding us back, right? Okay, so the gap here is going to be like, ideally, like rho n would be like, C over n for C, a constant, not too small. If C is too small, then we're going to fall back below that Keston-Stigam bound. Right? But ideally, we'd have this, but like spectral methods need more like rho n equals like log to some Cn over n, or even in some situations, something like root n sparsity. Okay, and I'll point out kind of when these two different situations tend to hold, if time allows, tomorrow. Okay? I think the example I'm going to show you tomorrow actually lands us in this domain, which we don't love, right? Like this is basically asking that like all the degrees in my network grow like root n, which is, I mean, that's not terrible, but it's pretty unrealistic, right? So this is not ideal, but it's kind of if you do all the easy bounds, the kind of stuff I'll show you tomorrow, just because they're things you can present in the space of a lecture, you land in this kind of slightly less strong bound. And then next week, Joshua will show you some of the tricks for getting these better kinds of rates. Okay? So this is the notion of sparsity. It's an issue here just from a theoretical standpoint, because we'd like to compare spectral methods with other methods for doing things like community detection, right? It's also an issue just for modeling, right? Real networks tend to be sparse. Like you go out in the world and you like find a network, like most people don't have a lot of friends, right? Like the average Facebook user has, I think back when people still used Facebook, had like 150 friends, right? And there are something like 2 billion people are or were on Facebook, right? 150 out of 2 billion is like not a big number, right? So real networks are sparse. I would like to account for that. Okay, we have 5 minutes. I want to spend, or not even 5 minutes, I want to spend 2 minutes mentioning something for the sake of mentioning it, because like you're going to see it if you go and read this literature more. But going into detail about it is sort of outside of the scope of what I want to cover this week. It's a little odd to have to take this matrix and scale it down by rho. And I'm going to highlight the fact again, remember, rho depends on n. Okay? Why is that awkward? We lose an important property that I think we all mostly like when we're doing probability, and that is projectivity, right? If I see a matrix A, and it's this big n by n thing, right? If I form A tilde, right, so like A tilde equals the induced subgraph from 1 to n minus 1. And I hope this notation is reasonably clear. Right? I look at A, and I look at the subgraph induced by just the first n minus 1 vertices. So I look at like that top left n minus 1 by n minus 1 block of A here, right? I get a new matrix A tilde. I'd really like A tilde to be equal in distribution to an RDPG with like rho n minus 1 times x, and I'll write x n minus 1 to stress that there are n minus 1 of these guys. Sorry, my handwriting is getting progressively bad over the course of this afternoon. Right? Reasonably clear here? Two different ways I could generate an n minus 1 by n minus 1 matrix. Either I could draw from an RDPG with sparsity parameter rho n minus 1 and n minus 1 latent positions, or I could generate an n vertex graph, and throw away the last vertex. Okay? Two different ways to generate a network on n minus 1 vertices. And the problem is, I'd like this to be true, but it's not true, because this guy had sparsity parameter rho n. This guy has sparsity parameter rho n minus 1. Okay? So we lose projectivity. Now, who is bothered by this? I mean, it's annoying if you're like trying to do mathematics sometimes, right? Like, suddenly, you know, Kolmogorov extension theorem is like not quite on the table anymore, which is always a bummer, right? So this is a bit of an issue here. If you're a statistician, I don't know, it depends on kind of your philosophy, right? But as an issue I want to highlight, I also want to highlight that this issue is not unique to the random dot product graph. This issue is baked into all models where A has the same distribution as, let's write capital pi A, capital pi transpose, where capital pi is a permutation matrix. So any matrix that has this property called node exchangeability, basically I can shuffle the rows and columns of A and I haven't changed its distribution. All models that have this property are going to suffer from the same issue. They generate dense networks. You have to let rho n depend on n, else you cannot generate dense networks. Excuse me, you cannot generate sparse networks. And this was actually alluded to during Carla's talk on Monday, I believe it was. Right? The graphon is a more general version of this network, but all networks that have this kind of property are going to be dense. So we have to do something like this, else we have to give up this nice node exchangeability property. And there are papers that do that. We're not going to talk about them this week. Thank you all for your time and attention. I will pick up this thread tomorrow. We'll come back to how exactly are we going to evaluate our estimate of x, and we'll incorporate sparsity into that story. Thank you all so much. See you tomorrow. And we are 30 seconds late for coffee, so once again, you will not hurt my feelings if you run out of the room and get coffee. I also will stick around and happy to answer questions. Thanks.
I thought I'd just comment that since many people here have done or do random graphs of or this random kind, we're sort of all used to these parameters we go to zero.
Yeah.
But yeah, it is a bit of a philosophical issue.
Yeah, so it's always nice to have Kolmogorov extension theorem, these kinds of things, right? When you don't have it, things get annoying. Like, you always want in the Erdős-Rényi to be able to just like, what if I add just one more vertex? And like, yeah, if p is going to 0, then like you can't do that, right? Yeah, good point, thank you. Also, for those who are curious about the impossibility proof, it's sort of fun, so that you can, so the proof, you know what, I don't want to embarrass myself and have to recall this on camera, but like, there's a clever trick whereby you basically use Kolmogorov extension theorem to show that like, if you are sparse, then you can't be in one of these models. Don't make me recite it offhand, because my memory is not that good. I should mention, just while I still have the camera on me and everyone's mostly still paying attention, those results I alluded to about these exchangeable node models having necessarily being dense is due to work by Aldous and Hoover, Aldous in 1981 and Hoover in 1979. And if you want to see a really nice treatment of that, more recently there's the great book that I think most people in the room probably already know, Laszlo Lovas's book on graphons. Okay? And that's 2012. Just figured I should mention that because it is a cool proof to see once in your life. So this is the famed exchangeable array results, basically the matrix version of De Finetti's theorem, which is pretty neat. Okay, now I'm actually done, so thank you all so much. All right, now we're